Thanks for being here. I'm very excited to be here today because I'm going to be talking about some of my by far favorite things, meaning music and instruments and dogs and how I married it all together with my favorite tool, which is Python. And I'd like us also to see what it's like to deal with processing music in real time in Python. Throughout the talk, I would want us to build a musical instrument and see what challenges we encounter on the way, and also see which features of the programming language help us or stop us from solving them. But before we delve any deeper, let me briefly introduce myself and give you some more background on how I developed interest in the topic. So I'm from Poland, where I co-founded the Polish chapter of PyLadies, and around the same time started attending a lot of conferences, getting closer to the Python community, which I really grew to love. And sometime last year, or a year and a half ago, I became the managing member of the Python Software Foundation, and I'm gonna use this opportunity of being on stage today to encourage you all to register as members of Python Software Foundation. Like, just by being here, it already means you are a part of the Python community, and each of you can register as a basic member. I encourage you all to do so. And please consider applying to become a voting member, managing member, if you support the Python ecosystem for at least 5 hours a month. It can mean contributing to an open source project, or being involved even in any of the educational initiatives, or organizing events, and so on. Please refer to python.org for more details and registration forms. Okay, so I don't live in Poland anymore. 4 years ago, I moved to Germany to start working at the music tech industry at a Berlin-based company called Ableton. At Ableton, we make software for music makers, and for all sorts of music makers, starting from bedroom producers to professionals who take our software on stage to perform live. Hence, the name of our flagship product is Ableton Live. As a kid, I like to say that I was gonna become either a scientist or a guitarist, so I think I landed somewhat in between. But actually, my musical encounter started way before I started shredding on my guitar as a teenager. And my first musical instrument looked something like that. And, okay, it may not look like much if you think about it on the first glance. I actually thought my parents didn't take me seriously when I said I wanted to play on the keyboard as a kid. But I grew to love this one, especially the dog sound. You could play it melodically on the keyboard, great. And so you may think it's not very serious, but there's a long history of experimenting with tools for music making that actually made it possible to enjoy these toy pianos that make silly animal sounds today. So what is a toy piano like that? Turns out it's a very simple version of an electronic instrument called a sampler. Well, these may look a little more serious, maybe you know them. To be fair, they're not so far off. So what is a sampler? A sampler is an instrument which plays back a pre-recorded sample. Pre-recorded sound is going to be called a sample. We're going to refer to it by this name. It can be any sound imaginable. It can be a sound of a classical instrument, you know, like piano or trumpet or cello. Or it can be a part, sorry. It can be a part of the song you like, or any, like a sound of a scratching surface, audience clapping, a car passing by, whatever you record on that. So I'd like us to build one of these. So in order to better understand what samplers are, how they are used, let's take a minute to touch on the history of sampling. It all began in the first half of the 20th century when a tape recorder got invented. So a tape recorder made it possible to record all sorts of sounds. So a composition style emerged around this idea, which used very different tape manipulation techniques to change these pre-recorded sounds. So musicians started cutting magnetic tape and flipping it over, or a part of it over, and gluing it back together, looping it, playing it back at different speeds, and so on. So that opened completely new ways of experimenting with music making. Composers started focusing on shapes and envelopes of sounds, not just timbres. So in the 50s, it was fashionable all over Europe to make music out of unusual sounds and repurpose them for different reasons. So anything, as I said, anything that could be recorded on tape and could make sounds are being used in compositions. And that technique, that art of composition was called musique concrète. So the idea of playing with magnetic tapes was taken a bit further, and then in the 50s, the Chamberlin and Mellotron got invented. The Chamberlin in the 50s and then Mellotron in the 60s. So the Chamberlin was the first electromechanical keyboard that played sounds recorded on tape. So that's interesting. It was very expensive, and only a limited numbers of them were released in the US. So then, in the 60s, its successor, Mellotron, appeared on the European market and started being mass-produced. So what's interesting about this instrument is that when you press a key, actually a sound recorded on a strip of tape, magnetic tape, gets played back, and then when you release the key, or when it's finished, a string attached to the other side of it just pulls it back in place. So that was the first attempt at creating these melodic samplers, playing back recorded sounds. The standard version shipped by the manufacturer had 3 different sounds recorded on one strip of magnetic tape. There was a sound selector that you used to change between them. And there were the sounds of flute and cello and violin. If you wonder what it sounds like, think of the Beatles' Strawberry Fields Forever. These like flutes there, it's actually mellotron. So while Europe was all about cutting magnetic tapes, at the same time, DJs from South Bronx in New York City developed a very different approach to sampling. So they didn't record sounds they liked to manipulate them and use them in their songs. They actually created these samples live by very skillful vinyl manipulation. So they started speeding records up, slowing them down. Around the same time, they came up with the idea of scratches. And interestingly, to loop a sequence they like, they started bringing 2 turntables to shows and started playing a sequence they liked on one turntable. And then when it was about to be finished, they would fade it out and slowly fade in the same sequence on a different turntable. And so that was sort of crude and not like easy to do. So that thing actually led to the development of crossfaders between 2 decks that DJs use nowadays. So the all was really cool and nice, but as I said, sort of crude. So a natural need for better tools for this sort of sound manipulation emerged and led to the development of the first samplers, which are closer to how we know them now. And that was a big step. Portable digital samplers really increased the accessibility and potential of sampling. It was easier to record sounds. You could record multiple sounds in it and trigger whatever you want. You could easily manipulate them, and the whole era of sample-based music started to be a thing, which is up to these days, actually, the most popular technique while making pop music. But these first units were actually expensive and not accessible for everybody. So Casio tried to change that with their series of cheap keyboards with only very basic editing possibilities. They allowed you to record your own samples, but very short ones, a little bit less than a second and a half, and in very low resolution. So it's like also a very interesting thing about this is that these devices only had volatile memory. So you could record your sound with a built-in microphone, manipulate it, play with it, and we switched the device off, it was gone. So that's Casio advertised their keyboards as toy keyboards for all these reasons. But still, musicians fell in love with their very characteristic lo-fi industrial sounds. So the SK5 can be heard nowadays in songs you recognize and know. But speaking of toy keyboards, well, one step forward and we arrive home where we started at our amazing device. Well, now we know that all that had to happen for it to be possible, right? So I thought it would be fun to build something like that in Python, since I wanted to see what it takes to build a playable musical instrument. And I thought it was nice and fun, despite its very limited feature set. So our application, just like this device, is only going to be playing back a pre-recorded sample. It will not have recording capabilities, which also means it can be referred to as a rompler. Rompler stands for ROM, read-only memory, and sampler. So it's a rompler. So it will allow us to play back the sounds at different pitches, melodically, and also allow for some basic gain adjustments, which are going to translate to a perceived change in loudness. There's another thing that inspired me to go this path and implement this device, and it's my favorite four-legged friend called Chico. It's a dog that used to hang out in our office in Berlin. It's my colleague's dog. Unfortunately, moved to New Zealand last year. So I sampled Chico. This is how it sounds. Say hi, Chico. This is going to be our sound. So let's have a look at what we were aiming at. So I'd like to introduce you to Subwoofler, or in other words, a barking sampler. And let's see how it works. Okay. This is Chico. You can play it melodically, as I said. Yeah, I guess whatever song imaginable you can play in one octave, you can go have a look, give it a go. And speaking of these slide manipulations that I mentioned, here is you can switch on a feature that will change the loudness of the sound in with some frequency. And don't worry if you don't understand how it works now, we'll talk about it later. But basically, when triggered on, it makes our sample sound like this. Fade out and fade in. I'm just pressing the same key in the same way all the time now. And then we can change the frequency of this change. Like when I increase it, maybe I'll increase it slightly first. So it's going to start fading in and out faster. But if I go one step further and actually change the frequency so that it cuts through the sound, you can accomplish very interesting results with such a basic manipulation. Or right? So such a basic adjustment allows us for it has a very creative potential. So that's Subwoofler. Now let's see how it's made. Let's see what components it's made of. So this is a simplified, higher-level structure of the application, which shows the basic process flow. So what we do is we press the key, right? We need to figure out how this key, like A on a keyboard, translates to a musical note. Then think of ways that in which we can actually make sure we play back our barking sound at the right pitch. So these are the three things we'll have to figure out how to do. I structured the application into three logical parts. The first one is an I/O unit, which is a part of a graphical user interface as well. And in this application is handled by TKinter. So this GUI is written in TKinter. And then the next unit is the audio processing unit, which gathers the user input that is sent to it from the I/O unit and makes sense of it. Meaning it has to interpret so that it knows how to manipulate the sound accordingly. Then, once it's manipulated the sound, it's going to pass it on to the player, which then will have to figure out how to make sure the sound makes it all the way through the chain to the speaker so that we hear the sound. So let's have a look at each of the units separately. Well, the I/O unit, as we said, it was responsible for detecting the KEYPRESS events and translate it to something musically relevant. So it will have to translate a keyboard key to a musical note. How can it be done? Well, it turns out there is a standard defining this sort of exchange of musical information across devices and instruments. This standard is called MIDI. It stands for Musical Instrument Digital Interface. MIDI basically encodes musical notes to values it understands. So every musical note is assigned a value, and usually the middle C on the grand piano corresponds with the value 60. The range of values accessible for us is from 0 to 127. And then each consecutive value refers to the next semitone. So if we said that 60 referred to the middle C, 61 gonna be C sharp, 62 D, 63 D sharp, and so on. So we have 128 values to encode the musical notes. And since there are 12 semitones per octave, it means we can encode up to 8 octaves. Okay, so in summary, our I/O unit listens to key presses and maps them using just like simple mapping with MIDI note numbers. That's all it does. Then it passes that MIDI note onto the audio processing unit, which has to prepare the sound to be played by the player. So the audio processing unit is responsible for two major things, meaning it has to know how to read an audio file and store it, and then figure out how to change the pitch of the sound. So by changing the pitch of the sound, I mean, remember Chico? Chico is positioned here. This is the original. I'll switch off the effect. This is the original Chico sample. Anything, every note I press to the right is like pitched up. It's transposed up, and everything I press before it is is like transposed down. It's a tiny dog, right? It's very highly pitched. Yeah. So let's go back to the presentation. So this is what the audio processing unit will have to figure out, how to accomplish that. So let's take a look at how the bark sound is loaded and stored. So we want to essentially take an audio file and store it in memory as a sequence of numbers. Well, it turns out that dealing with sounds is essentially dealing with large arrays of data, like dealing with any other signal. Our audio file is stored in the wave format. So to read it, I use the built-in wave library. Did you know there was a built-in wave library in Python? That was a big surprise for me. But it's great. It's not easy to make sense of it. The documentation sort of assumes some of your knowledge, so I ended up reading the source code to make sense of it, but it's there. You don't need any external dependency. So a wave file consists of some metadata information and then a sequence of numbers. But you have to know how to make sense of them. So in order to know how to interpret them, you actually need to know how they got obtained by recording the sound through the microphone. So at the recording, we are dealing with a continuous analog signal coming to the receiver, a microphone, and we read one of its value at a time at equal intervals. So an analog signal has an infinite number of values that we could read, right? We have to decide how many of them we actually want to read and store. The more we obtain, the higher fidelity of our sound is going to be. But then it means we'll have to deal with the higher memory footprint and more operations on that data to be performed. Oh, like more data to perform operations on. So we need to keep our balance, like make a decision that works best for us. Then there is a different thing that we need to decide on. We need to decide on how many bits we want to store these values on. This parameter is called bit depth. On this picture, you can see that every value is assigned a number from 0 to 15, meaning there are 16 possible values to encode our information on, which means the bit depth is going to be 4. So it makes most sense to store arrays of audio data in a numpy array in Python, because we can immediately specify the data type we want to use. We have to decide if it's going to be 8-bit integer, 16-bit integer, and so on, depending on what got decided while recording this audio. And thanks to that, we also get the guarantee of allocating a contiguous chunk of memory for our data, which is fast to iterate on, and we also get that access to all the convenient vectorized operations we can then perform on this data. So as we can see, we just basically read a value at a time and end up with an array of numbers. This process of obtaining these values is called sampling. We obtain a sample at a time. And yes, it's confusing, because till now we've been referring to a sample as an audio file that you can actually sample on a sampler, right? That we can play back on a sampler. And I'm sorry, this is the world we live in the audio world. It is confusing. So it turns out that a single file, a single number, as well as a sequence of numbers, can be referred to as a sample. So the set interval at which we read our values, measured in seconds, is called the sampling interval, or period. When we divide 1 over it, it turns out it's called sampling frequency, or sampling rate, is measured in hertz, and it basically means how many samples we obtain in a second. So sometimes we'll be sampling a sound on a sampler, and that to obtain a sample, or we're going to be sampling a signal to obtain audio samples. So yes, we can sample a sample at a sample rate to get samples. I'm sorry. And for the purpose of this talk, I think from now on I'll try to refer to this sample on a sampler as an audio file, so that we don't get confused. And samples are going to be numbers in an array. Okay, let's get back to the overview of what the audio processor is responsible for. So it reads and holds onto the audio file, and now we know how. And then it needs to figure out how to change the pitch of the sound to the one requested by the user who pressed a key. So let's see how that is done. It turns out that when we play back a sound at different speeds, the pitch is different. It's going to sound higher or lower. And also there's that property that an audio recording, which is played twice as fast, is going to sound the full octave higher. And when we play it twice as slow, it sounds the whole octave lower. So maybe to illustrate that concept better, I recorded a video for you. I hope it's helpful. This is the normal tempo. Slow down, it's lower. We're going to speed it up. So I hope that maps your mental model a bit better of how things work. I'd like to thank the artists who let me use their music in this presentation. It's from the album Seine Svi. It's by Bendik Baksons and Kjetil Jerve. So let's get back to this phenomenon. This technique is sometimes actually called the chipmunk effect. It's because it was explored by the creator of the cartoon Alvin and the Chipmunks, who recorded his own voice on magnetic tape at half the normal tape speed. And then when he played it back at normal speed, it sounded the full octave higher. I recorded something for you to demonstrate what it sounds like in case you're not familiar with this cartoon. Sorry, that's a bit quiet. Yeah, so it's very highly pitched. It just basically my voice played back twice as fast. Okay. So let's take another look at the signal discussed before. When we tell a player what the original sampling rate was and give it the full array of numbers that we sampled and ask to play it back, it's going to just play it normally at normal speed. But then, what happens when we ask to play it at the same sample rate, but just jump over every other sample because we want it to play twice as fast? It's going to play half the number of samples, right? So it's going to go over the whole sample faster. So this phenomena also means that it shortens our sound. Okay, so our audio processing unit has to just basically figure out what the playback speed of the sound is going to be. But there's also one more thing that this unit is responsible for. It's these automatic changes, this is like the loudness that we explored. And in electronic instruments, this is something we refer to as modulation. You can just think of it as automatic changes to the sound applied over time. To better make an idea of what it's like, imagine turning the volume knob up and down. So you're playing with sounds, you're turning up and down, and your sounds changes, is louder and more silent. And then after a while you figure, well, I could be using my left hand for something else because I'm busy on at my decks, right? So you'd want to automate this movement. And when you think of it, maybe this movement maps to a shape you're familiar with. It's going to be like a shape of some sort of a periodic signal. And maybe this animation shows it better. Imagine this is our volume knob, and basically by turning it up and down, we generate a periodic signal. In our application, we are actually using a sine wave. So Subwoofler is modulated by a sine wave. But there are some other periodic signals that are very common in the electronic music world that are used as modulating signals, and these are the shapes of them, either a sine wave or a square wave, triangle, or sawtooth. The modulation is accomplished by using a low-frequency oscillator, and let's see what it means. So a thing generating signals is called an oscillator. A thing manipulating a signal is called a modulator. It's what we mentioned before. And typically, like all electronic instruments have a low-frequency oscillator that is used as a modulator. So why is it called this way? It's because the frequencies used to modulate signals are most of the time much lower than the frequencies we would use to generate sounds to play with. Also, signals that are from outside of the audible range are still useful, that modulators, but it wouldn't be useful for making music because they're below 20 hertz, which is like the beginning of our audible range for the human ear. Okay, so let's get back to our process flow and see what we've gathered all together. So now we know how to translate a press key to a MIDI note in the I/O unit. We know how to read an audio file, figure out what the playback speed is going to be of this file, how to apply modulation, and now we need to know how the player deals with playing back our sample. So we basically want to turn the array of manipulated data back into something that an audio driver can like pass on to the speakers. So that communication with the audio driver is handled by an external library called PyAudio. And PyAudio is basically a connection of Python bindings to port audio, a rather popular audio I/O library. So it works in two modes. It supports two modes. One is blocking, the other one is non-blocking. What it means, the blocking mode basically blocks the execution of the whole application for the time needed to deal with all it has to do, which is probably not what we want, because we want our application to be still reactive to the user input, to the user interactions. So imagine like a user plays a note, and even before the sample is finished playing, the user plays a different note. So we want to like immediately trigger a different note and also apply changes to the parameter instantly also. So this is why we don't process the whole audio file at once. We actually process it chunk by chunk. And this is what non-blocking mode does. It receives a chunk of our data and passes on to the driver and then waits for another one to be played. And a chunk of sound we process and play back at a time is called a buffer. So this is the journey of the buffer from our audio processor to all the way down to the speaker. We pass it to the player, then it communicates with the driver, and the driver knows how to pass it on to the hardware. The buffer size in Subwoofler is 32 samples, and we want our buffer size to be small enough for the application to be snappy, but actually big enough to have enough time to prepare it on time. If the computer gets busy processing I/O operations, redrawing the screen, or doing many calculations, we may actually fail to deliver it on time. And what happens then? The audio hardware runs out of data to play. What it means, then it like plays data, and then there's this like sudden disruption. It breaks the continuity of the sound, and it results in this like very unpleasant crackling sound. It's called the dropout in the audio world. So we want to avoid that. We want to make sure we commit to delivering this audio buffer on time. In our application, the buffer size is 32 samples, and the sampling rate we used, the most common one, 44.1 kilohertz. So it means our buffer is not even 1 millisecond long, it's 0.7 milliseconds. Okay, now we can actually draw a complete process flow with all of the information we've gathered. In these like yellowish frames, I depicted what runs in its own thread. So we have 3 threads here. There is a main blocking thread responsible for handling the blocking I/O operations. There's an audio thread responsible for applying like all the modifications to the sound. And there's also that player's thread spawned by Pi Audio that is used to communicate with the driver. So that's all. This is how the application is built. Now let's wrap it all up, what we've discussed today, and see what challenges we encounter while dealing with real-time audio applications. And let's see what properties of a programming language actually matter here, and why some programming languages are more preferred here than the others. Well, so every real-time application, as well as our real-time audio application, has to satisfy strict timing constraints. So as we said earlier, we really commit to developing, to delivering that audio buffer on time. Because we know what happens. When we have a lot of dropouts, our sound quality is like, it's not good. We're not doing a good job. It's like our instrument is gonna sound bad. So predictability is important here. We have to know if we actually can commit, if our buffer size should be maybe bigger. So this is when the garbage collection is a big red flag for audio developers. It's because a garbage collector is gonna log at runtime to collect and clean up. And we may not be able to sacrifice 2 milliseconds of our time for that. So basically, languages without garbage collection are preferred. But since it's there, we can deal with it, but we should at least know what it's doing. We have to know how to prepare for its execution and when. So basically, to alleviate this problem, make sure you manage the lifetime of your objects carefully, that you avoid cyclic dependencies, because generational garbage collector is harder to track. Then it would be actually nice to run some operations in parallel and make use of all of our cores. We can do that with CPython, but also some languages provide ways to ensure log-free atomic data exchange between threads, so we don't get that overhead of context switching. CPython, unfortunately, doesn't provide us with that. Also, interestingly enough, it turns out that in audio applications, memory I/O operations can be a severe bottleneck, sometimes even more so than the CPU-heavy operations. With Python, we don't have the full control over the memory layout, so we actually can be as cache-friendly as we would want to. Also, last but not least, we don't get direct access to all the machine-level, low-level optimizations, like vectorized computations. So we're really like not making the full use of our CPU. Well, that all actually only applies to dealing with real-time audio applications in the end. So if you just want to deal with audio in Python offline, and by offline here I mean not in these in the reactive way, not in real time, then you don't need to worry. You can just do it. So this is why I like to use Python to prototype and measure things, and I think Jupyter Notebooks is also a great tool for exploring some things. So I encourage you all to have a look and play around with it. The code is on GitHub. I really hope it's easy to install. It has only 2 external dependencies. The rest is vanilla Python. Should be lightweight. As I mentioned, even the user interface is written in tkinter. So that's all I had for you. But before I finish, I'd like to thank all of the amazing people who made it possible for me to use these beautiful icons on slides. And the dog is in the public domain. So I can have this logo. Yeah, that's all.
Can you play a song?
Sure.
Any question for the speaker? It's a really amazing talk. Yes.
Hi, thanks for the cool talk. I guess my question is very simple. Is Python, if you can answer it, of course, used in any sort of way inside of Ableton? I'm imagining maybe not in the DAW itself, or maybe in some VST, or is it, as the constraints you explained before, circling out of place and it's only C++?
I don't think Python would be ever the first language of choice for like real performant audio applications, real-time audio applications. But I still argue within my team, which is like a C++ team these days, that we should just I would really wish us to do more things in Python, just to prototype things. And I wish I could end up in a place where there would be more possible. And there are things out there to explore, because I think PyPy gives us with some potential, because you can deactivate garbage collector and you get JIT and so on. So this would be my next step. I will try to run it on PyPy. The Pi audio doesn't run on PyPy. I tried. Okay. So interestingly enough, I benchmarked the application and it runs faster by like 27% on Python 2 versus Python 3, and I don't know why. There's also something to maybe discover there. It could teach me something, like, you know, like point the places where to look for. So this would be my next step too, to like explore there. So yeah, there are some ideas out there of things that could be explored. I wouldn't be overly optimistic, but I'm sure we can get, you know, like we can get to a better place. Yeah.
Thanks.
Regarding the problem of the garbage collector, why use you can have some buffers and you can overwrite data in that buffer using modules like the struct module of Python without having to destroy the container of your data each time. You can feed the container, have the player read the data, and then you go back and overwrite the data. I don't know if you ever did something like different pages from video animation, when you have pages and you feed the page to the video card. The same you could do here.
Yeah, I agree. So I just wanted to make the point that people should be aware of what they're doing and do it. Like, it's not that you can just think that, okay, when you write in Python, you just have to have it at the back of your head, right? Oh, that's going to happen. So I have to actively go out there and do something in order to avoid it, right? So this was, I wanted to make this point. I agree that there are some things that could be tried, and I would be more than happy to see how far I can go. Absolutely. Yeah. Hopefully, maybe next year we can have a follow-up with all the measurements that happened. Yeah.
Any other question? Seems not. So thank you very much again, Anna. Oh, sorry.
Oh, yes.
Just last one. Thank you very much. That was really interesting. I think I remember the Casio keyboard from the 1980s, and if I remember correctly, whatever sound it sampled would always play it back as an A or a B or some particular note. Now, every or most sounds might have a kind of natural pitch to them, like the bark of a dog. Yeah. Would it be possible somehow to find out what pitch, the natural pitch of the dog's bark is, and then map that to its...
It would. Positioned it like by ear. It's it's something I extracted it as a configurable parameter. Actually, what the root node is, it's configurable in the application. I positioned it there because I liked how the full octave sounded. Well, yeah, it's easier to extract pitches of certain sounds than the others, like some percussive instruments wouldn't make much sense. But yeah, there could be another interesting follow-up on that, to like drop a sample on that and then find the right pitch and suggest a...
Is it easy to do is my question.
Easy to do? Like,
Easy.
I gave a previous talk about finding the right pitch that I can like refer to. Well, so the thing is that we would like get to the spectral domain and make like, we would just like increase the load of the application. So I don't know if it would still be playable, you know, but like that would happen not, yeah, before loading. So maybe we could just use that. Yeah, that doesn't matter. Yeah, I could just incorporate my two hacks together and see how that goes. Yeah, there's on my GitHub profile, there's that other code that does that. It doesn't have a catchy name. It's like real-time modo to MIDI, which basically one of the stages of doing that is finding the pitch of a note that's played. So yeah, there are techniques that are there, and I can refer you to it. It's it uses the capstral method to do that. Yeah. Yeah.
Any other questions? All right. So now, again, thank you very much.
Thank you.